In the previous class, we started a discussion on a generic approach to analyzing the fields associated with a wave in any direction. So, since we said that now our interest would be to investigate how waves propagate inside bound structures, so we must not ideally place any restrictions on where the fields can lie. So in general, if a wave is traveling along the positive z direction, in that case ideally we would expect that the fields would lie on the transverse plane, that is the plane perpendicular to the z direction, which is the xy plane. But because of the reflections associated with the boundary walls of guiding wave structures, some field components can also exist along the z direction. So we had said that let's first solve for the longitudinal fields, that is the fields along the direction of propagation, and using those longitudinal fields we will solve for the transverse fields which are along the x and y directions. So we had said that the longitudinal fields are the Ez and the Hz. So we had started with this assumption that let Ez be a function of x, y and z, and we used the variable separation technique to write this as a product of three functions: some function of x times some perhaps different function of y times some different function of z. And we had said that the z component will consist of a traveling wave or traveling field, while the x and y component would consist of standing waves or standing fields. So we had seen the three equations which were second order differential equations, and they are rather similar to what we had got in the case of the transmission line or the wave equation. So the fact, or rather the interesting point to note is that the nature of the three differential equations are very similar to each other. So in general, the nature of the solution for the three can also be the same. So if you recall, the let us say for the three of them, the equation was something of this kind. Where a is some constant which we had put. And last but not the least, the only thing is we had made the associated term with this as beta square. Now this beta is not the beta of the wave that is entering the waveguide. This beta is the wave of the or the phase constant of the wave. This should be z square, just be careful. This beta is the phase constant of the wave that is ultimately being guided along the z direction. So this is very similar to beta prime. Now the reason I am writing beta and not beta prime is that we are now not going to talk about the individual wave, but rather the beta of the whole wave that is being guided along. So here note so this is very, very important. So we had said that let us choose solutions for the x and y components which give us standing fields. So therefore we got something of this kind. And in this case we shall choose the exponential solution because that is what is going to constitute a traveling phenomenon. So therefore we had chosen Fz as this way. So that is what we had done. So as you know, we had started with the assumption that let Ez be a product of three functions which are some unique functions of x, y and z, and this is what we have got, the three functions. So therefore now we can say that Ez will be nothing but the product of fx, fy and fz. So let's put this. And that is equal to the product of all the three solutions this will be y. Once again, this beta is the phase constant of the wave that is being guided, not the wave that is incident. So now this big expression is the generic solution for the Ez. So now let us not forget what the bigger picture is. We had said that let us try to define or solve for the fields which are inside a rectangular waveguide. So we had said that let the z direction be this along which the wave is guided. So remember, this rectangular waveguide is now a one conductor system. So this is the x-axis, this is the y-axis. So we had said that this is 0, this is x equal to a, and this is y equal to b, where the cross section of this waveguide is a rectangle, and you can say that in general A can be more than B. So now remember that this Ez is along the Z direction, so it can exist this way. So the question is, now can we do anything to simplify this? Yes, we can. We can apply the boundary conditions on Ez. So if you now see, the Ez is existing along the Z direction. I have shown it this way. It can be this way also in general. So what is now interesting to note, that this field will obey some boundary conditions at each of these walls. That means when either x is 0 or x is A, you have walls. So the boundary walls so essentially with respect to the Z field, it will see 4 walls. One is x equals 0, that is this wall. The other is x equals A, which is this wall. This is the x equal to A wall. The other will be y equal to 0 and y equal to B, that is this wall and this wall respectively. So if you notice, as far as the Ez field is concerned, each of these 4 walls are those on which the Ez is the tangential field. So here I can say Ez is a tangential field for these walls. That means at each of these walls, the Ez component must die down to 0. So therefore, Ez must be identically 0 at each boundary wall. As simple as that. So now let us say that this waveguide is infinitely long. This waveguide is infinitely long. So that means out of these terms, these 6 basic terms corresponding to C1, C2, C3, C4, C5, C6, which one of these terms will not exist if this waveguide is infinitely long and suppose a wave is starting to be guided along the Z direction? Well, I can say that there will be no reflected wave, because until I reach the end of the waveguide, there will be no reflected wave. So therefore, I can say that single wave implies C6 becomes identically 0. There is no reflected wave at this moment. So therefore, we will make our life little bit simple. So therefore, this one we are eliminating out of the equation. So now what? Now we need that when x becomes equal to 0 and y becomes equal to 0, the field must essentially be 0. So that is like saying some more components in the Ez field must die out. So when x becomes equal to 0 and y becomes equal to 0, C2 and C4 will anyway become 0 without any effect, because this is a sine term. So therefore, I can say when I put the boundary condition at x equal to 0 and y equal to 0, I should also have Ez as identically 0. That means at this boundary condition, Ez will reduce to C1 cos AX times C3 cos BY times C5 e raised to minus j beta z. So if I now substitute x equal to 0 and y equal to 0, 0, what I will get? These cos terms will become 1. So C1 times C3 times this traveling wave will become 0. So what I need is at x equal to 0, y equal to 0, this Ez term must be 0. So this can only be satisfied when C1 equals C3 equals 0. So C5 cannot be made 0 because otherwise the whole wave will die down. And that is what we don't want. So therefore C1 is equal to C3 is equal to 0. So this is necessary. So therefore in two shots we have eliminated C1, C3 and C6. So in general now I can say that Ez will be of the form of some C2 C4 C5 sin AX times sin BY times e raised to minus j beta z. This is the general simplified form of Ez. Now are we forgetting something? Are we forgetting something? Yes, we are. We are forgetting about what will happen at x equal to a and y equal to b, where we can apply the second set of boundary conditions. So at x equal to a and y equal to b, again we need to have the Ez dying down to 0. So now what to do? Now we cannot place, we already have proved that C5 cannot be 0. Otherwise the wave will die down. C5 cannot be 0. Now if C2 and C4 become 0, again we are not helping the problem. If C2 and C4 become 0, again the entire Ez field will die down irrespective of the boundary conditions. So now depending on whether we are looking at the x boundary or the y boundary, we can make either of the sign terms go to 0. So that is like saying when x equals a, then this sign term becomes 0. A times small a, that is 0, which means this argument a times small a should be some multiple, let us say m times pi. Now again we are introducing back the concept of m. Now again when y is equal to b, this sign term will die down to 0. Now this will imply that b times small b will now be some integral multiple of pi, which need not be equal to m. So let us put it as n, because in general small a and small b are not equal. So therefore looking at these two equations, I can say that capital A equals m pi by a and capital B equals n pi by small b. So now this coefficient C2, C4, C5 is a coefficient which is a product of three constants. So therefore we can group them and call this as one constant C. So now let us write the general form of the Ez after applying all the boundary conditions. So we get Ez is equal to some C times sine of Ax. Now we already know what is A, that is m pi by A times x, sine By, which is n pi by small b times y into e raised to minus j beta z. So now let us, we had started with the discussion in the previous class that let us solve for Ez assuming Hz is 0. So Hz is 0, which implies this is a TM mode of propagation. The transverse magnetic propagation, where there is no component of the magnetic field along the direction of propagation. So now we know that the longitudinal magnetic field is 0 and we have got a general expression for Ez. So without any further information, we cannot find what is C. So let us leave it like this. It's fine. This is some constant of proportionality which need not play much of a role. In general, what is important is the sign terms and this term. So now we had established already the method where using the longitudinal fields we will calculate the transverse fields. So let's do that. Let's apply those equations. So we had said that using Ez and Hz we will get Ex, Ey, Hx and Hy. There were 4 expressions. So if you remember, we had expressed them in terms of beta, which would be something like this. This is Ex, Ey comes out to be and Hx was j omega epsilon by h square d Ez by dy minus j beta by h square dHz by dx. And this is minus j omega epsilon by h square d Ez by dx. Yes, minus j beta by h square dHz by dy. So one thing we can say is that Hz is 0. So therefore this term, this term, this term and this term will get nullified. So by substituting what the fields are in the remaining parts of this 4 equations, what we will get is we have to essentially differentiate the EZs with respect to X and Y. So by doing that, what do we get? So for TM propagation, we will get Ex will be minus J beta times C. The derivative of a sine is cos, so we will get cos m pi by a x times sine n pi by b y times e raised to minus j beta z. Ey will similarly become minus jb beta by h square times n pi by b times c sine m pi by ax cos. Now this one would be differentiated, so hx would be j omega epsilon by h square n pi by b c sine of n pi by ax cos of n pi by by e raised to minus j beta z. And finally hy will be minus j omega epsilon by h square m pi by a times c times cos m pi by ax sine n pi by by e raised to minus j beta z. So notice that each of these field terms also have this e raised to minus j beta z term. This indicates that these fields are definitely contributing to the wave propagation because they are dependent on Ez. Now don't confuse the Ex, Ey, Hx, Hy fields with the expression that we had taken for Ez. This and this have nothing to do. This is for Ez only. So we had taken this expression and solved them using standing fields and traveling fields based on the direction that we are looking at. So do not confuse these with the Fx and Fy. So this is what it is for Tm. What about Te? What about Te? The T propagation in rectangular waveguide. So in TE propagation, as you know, there should be no electric field component along the direction of propagation. So Ez must be 0 while Hz is non-zero. So again, if you substitute or if you solve for Hz in a very similar way like we did for Ez in case of Tm, you will see that the nature of solution for Hz will be of a very similar form, which will have some constants in terms of, let us say, d1 as some constant. this is what it will look like. So again we can make D6 as 0 and remove this term, and we can again try to apply the boundary conditions. But now there is something very tricky. Why? Because if I have the rectangular cross section, this is Z, this is Y, this is X, this is X equals A, this is Y equals B. So if I were to now apply the boundary conditions on HZ, which could exist like this, the HZ will be like a tangential field along all of these waveguide walls or the boundary surfaces. But like how we took for Ez in case of TM mode, and we made that Ez as 0 because we know the boundary condition for tangential electric field. But the boundary condition for tangential magnetic field is not so simple. It will not be 0. It will not be 0. What will happen essentially is that this HZ will give rise to some surface current on each of these walls. So therefore, directly applying boundary condition on HZ is not going to be easy, because we will do nothing to nullify these constants. So what to do? So therefore, one of the best and only way is to take HZ as it is and substitute in those equations we had derived and obtain the X and Y components of the E and H fields, and then apply the boundary condition on those fields. So we can say use this to the Ex, Ey, Hx and Hy fields Alright, so let's first look at Ex, whatever Ex is. So this is the x-axis. So the Ex essentially exists along this way. Ey will exist over here. So since Ex is existing along the x-axis, it is a tangential field for two cases, when y equals 0 and y equals b. So I can say Ex is a tangential field for y equals 0 and y equals b, these 2 points. So what can I say? So therefore definitely some term over in the second bracket will get nullified. So if Ex has to be 0 at these 2 points, so what can I say? What can I say? I can say that looking at looking at the expression for Ex, you will essentially get some form of this Ez which will be used to represent Ex. So actually not this bracket for Hz, but rather the corresponding bracket which you will get for Ex. So what is that? Let's find it out. So let's go for Ex. So what we can say for Ex is, so Ex will be something like this. It's nothing but minus j omega mu by h square dHz by dy. So essentially what will happen is that in the hz term only this bracket will get affected. So if you differentiate with respect to y, this cos will become a sine term and this sine will become a cos term. So when y becomes 0, this anyway becomes 0. But for the field to die out, in that case, then the d4 must be made 0. Because the d4, now by differentiating, we will get d3 sine term plus d4 cos term. So therefore the cos term must go to 0. So what we can say, from this you can easily prove that d4 will identically become 0. Likewise, if you now look at Ey, that is j omega mu by h square dHz by dx. So what will now happen is that if I differentiate this, I will get a d1 sine term plus d2 cos term. So in that case, for Ey to be 0, at x equal to 0 and x equal to a, we will have to put d2 as 0. Because for these two walls, the Ey is now a boundary, or the Ey is the tangential component. So the Ey will exist like this, which at these two walls will be a 0. So that is how it is. And so therefore we have proved that d2 and d4 should be 0. So likewise, we can also say that at y equal to b, once again you can prove that this capital A and small b will be like this, very similar to the case of Tm. So using these, just like how we proved for the Tm case, we will get Hz is equal to d1, d3, d5 cos ax cos by e raised to minus j beta z. So this again I can write it as some d constant times cos of m pi by a of x cos n pi by b y e raised to minus j beta z. And already we know how to solve for the ex, ey, hx and hz. So let's write those down. So Ex will be j omega mu by h square d n pi by b cos m pi by ax sin n pi by by e raised to minus j beta z. Ey will be minus j omega mu by h square d m pi by a sin m pi by ax cos n pi by by e raised to minus j beta z. Hx will be j beta by h square times d m pi by a sin m pi by ax cos n pi by by e raised to minus j beta z, and finally hy will be j beta by h square d n pi by b cos m pi by a x, this is m, sin n pi by b y e raised to minus j beta z. So this is what the fields look like. Again, since these fields contribute to the wave propagation, all of them have some e raised to minus j beta z term. So lest we forget what we had started with, there is a wave which is entering the waveguide, which is the intrinsic wave. Now I am not at all bothered about what is the angle the wave makes with which plane and how many reflections it undergoes. All of these have been absorbed into the expressions which we have derived. So therefore, for this intrinsic wave, which is not bounded initially, the phase constant of this wave is omega under root mu epsilon, as you very well know. But we had defined that the beta for all these expressions is not this beta. Now this beta corresponds to the beta of the wave that is ultimately being guided along the z direction. Okay, so that may come as a result of multiple reflections inside the waveguide. So we had essentially proved a relation in the previous class, that is beta square is omega square mu epsilon minus h square, where this is the phase constant of the intrinsic wave, or the wave which is entering the waveguide, which is unbounded initially. So, or the phase constant of the wave by itself without considering any boundary walls. So now, what can we say looking at this expression? So can I derive an expression for h? So this gives me h square is omega square mu epsilon minus beta square. So by looking at the expressions or the for the fields which we have derived, by looking at the expressions for the fields that we have derived, you can actually prove that you can actually prove that this h is nothing but under root of m pi by a whole square plus n pi by b whole square. Prove this. This is something you need to prove. So now, once we have this h, which is nothing but the difference essentially between the phase constant of the intrinsic wave versus the phase constant of the wave that is actually being guided along the z direction. Let's come back to this expression, and we now can say that what can we say? We can say that the beta of the guided wave, which we had got as beta square, is omega square mu epsilon minus h square. So this is nothing but omega square mu epsilon minus this quantity. Now what we want is that this quantity beta should be always positive, so that the wave is traveling along the z direction. So if I now have beta more than 0, what can I say? So beta must be more than 0, which means this first term, for beta more than 0, I will need omega square mu epsilon should be more than this quantity. So that's like saying, if I define something called as the cutoff frequency again, I can say that the frequency of the wave that I want to pass must be above a certain value. So therefore the cutoff frequency let's call this as fc. That will be nothing but, just take this down, and with the 2 pi, 1 by 2 pi under root mu epsilon times under root of this whole quantity. So we always need f should be more than fc. F should be more than fc for the wave to propagate. So just like in case of parallel plane waveguide, even rectangular waveguides have a cutoff frequency. So now, in case of parallel plane waveguide, we saw that in general, when you have the concepts of m and n, it gives rise to something called as dispersion or dispersive mode of propagation. That means all possible frequencies cannot be passed, and the wave will essentially travel with a velocity that is not equal to its intrinsic velocity. But in case of parallel plane waveguide, there was a case when there was no dispersion and that was essentially the TEM mode of propagation. So that is something which is very, very ideal. The question now with which I shall leave you to think is, can we have any dispersionless mode of propagation in case of the rectangular waveguide? Now, one thing to note is that how the parallel plane waveguide had only one M, the rectangular waveguides are denoted by two mode numbers, M and N. So therefore, whether it is TE or TM, you must always write a small m, small m, small m, small m. So there are now two numbers which tell you the mode of propagation. Okay. So that is what it is, and with this I shall stop today's class and let you think a little bit before we meet in the next class. Thank you.